Hello, everyone. Welcome to the Art of Problem Solving session in this conference. I'm Shenhui Yang. I work for Wolfram Alpha. And then during my work time and probably outside work time, I like to solve many interesting math problems from all kinds of magazines, just like you've seen in the description. So today I'm going to extend it what I have done in the past year about Olympiad geometry. So this year we would like to give you a little more about like IMO feeling. So you have problems from different sections like geometry, combinatorics, graph, number theory, and we have a little more than algebra. It's asymptotics. It's like analysis and like Taylor series for a little bit more elaborated mathematics topics, and we will see the details about that later. Okay, if you want to check out the last year's topic on Olympiad geometry, feel free to go to the notebook archive webpage. You can download everything there you need. Okay, let's start. So the first problem I want to talk about is related to recently added functions in Wolfram Function Repository. It's called a circle inversion. So if you are familiar with kind of advanced level problems in Euclidean geometry, you probably have heard of this topic. It's basically giving you sort of a conversion between circles to circle, line to circle, or point to points, and usually give you a very good insight into very difficult problems. And in this example, I'm going to talk about quite a beautiful sort of like a lemma or theorem about circle inversion with respect to some important stuff like a circumcircle, incircle or incenter, and the 9-point circle of a contact triangle. So the statement states like the inversion of a circumcircle about incenter is the same thing as the 9-point circle of the contact triangle. Let me show you the demo. Okay, if you have a reference triangle, it's in gray, and I plot a large circle that goes through all the vertices. And you have a circumcircle, and the yellow one is the incircle. And you drag it around, and there is a contact triangle, and this small blue circle is the inversion of the larger circle with respect to the yellow circle, and it is the 9-point circle of the contact triangle. So it's a very beautiful theorem. And if you want to learn or refresh your memory about circle inversion, I have an application session here. It gives you all the useful information about the transformation between different objects. So you can always refer to that. And if you want a little more detailed information, you can go to the neat example session. It shows you some very important properties of circle inversion, okay? And we can also quickly, just to verify before we go into the proof, we can just quickly verify what's going on here. So if you have incircle, it's in, and the circumcircle, you just using one line function that directly converts incircle, the circumcircle with respect to the incircle, and to give you the image of this conversion. And also you can just define a contact triangle in this way, and then using triangle construct directly on contact triangle, and called the 9-point circle property, and it gives you the 9-point circle of this triangle. So this looks exactly like this thing, okay? So this basically proves our our statement. So let's just quickly go through the proof. It actually is quite beautiful and straightforward. Okay, we have a reference triangle, and this is the incenter. And we can easily see that ADIE is a kite and symmetric about the AI. And also we have ID is perpendicular to AB, and similar things, IE perpendicular to AC, because AB is a tangent line of this incircle. Now, because of symmetry, let's just take out this part and maybe rotate it a little bit. So look at the D here, A here, and I here, okay? If you take a look at this shape, we have a right angle here and a right angle here because, as I said, it's symmetry. So AI is the perpendicular bisector of this one. And because these two right triangles share the same angle, so we have a similar property, and the corresponding ratio between the sides and hypotenuse are the same. So if you move DI altogether and IM altogether, you have DI squared equal to IM times IA. And this is what we have for the definition of circle inversion, basically using the power. And if you look at these two, they are exactly the same. So this shows that M is the inversion of point A. So it's the same thing. It's B and inverse to this point, C inverse to this point. And let's go back to the definition of this 9-point circle. 9-point circle is defined by 3 sets of points. Every set you have like 3 points. So the first set is the orthocenter to the vertex and take the midpoint. The second set is all the foot of altitude, and the third one is the midpoint set. And on the other side, because given any 3 points out of the 9-point, you define the 9-point circle. So this is what we have here. We have a circle that passes all the 3 midpoints, which is absolutely the inversion of the larger circle. So this proves our statement, and we are done. There are many more important examples you can play around about circle inversion. So just feel free to go to this webpage and take a look at its stuff. Okay, we are done with the geometry part. Now let's move to combinatorics. So this problem was posted a while ago, and it's the date for the solution submit is already passed. So I think we are just okay to talk a bit about it online. So without a kind of impeachment. So the problem, if you have already checked out my materials, I uploaded like 4 days ago. So you can also just go back and simply put is this problem start with a statement that says Baker is not Baker, carpenter is not a carpenter, driver is not driver, plumber is not plumber. So this is closely related to derangements. So say giving you 3, 1, 2, 3, say we have 3 numbers. It's okay to have like 3, 1, 2, because every number is not in its origin position. So let's take a quick look at how you can program it in Wolfram language. There are also a derangement page for in MathWorld. You can take a look at it. The code I use here is from Stack Exchange, and it simply works like this. You have a pick in the out, that's the outermost function, and you have an index in the end. So pick function only picks up everything here is true. So it looks like a false, it won't work. Okay, it just does not pick this one. What the inner same queue does here, it compares this thing and this thing element-wisely. So you compare 1 is same as 1, 2 is same as 2, 3 is as same as 3. But 3 is not same as 1, 1 is not same as 2, and 2 is not same as 3, okay? So eventually you have a truth table about all the comparisons. And then you apply the NOR function here. NOR function says if there are anything true in the list, it returns false. So the only thing you can have true is everything like here, like a false, false, false. So this will give you all the like true, true, true here. So this one eventually picks out all the permutations that looks like derangement, okay? And then the second step is you want to generate all the valid derangements. So you just apply that to all the occupations, and you have a list of derangements. And I want to see if this result is correct or not. Just use derangement formula. It's here. It's m factorial over e and take the nearest integer. So it's 4 factorial over e, and you do round, you have 9. And I have 4 plus 4 plus 1. So it's 9 elements here. So it looks like correct. And then the last step is to compare my statement and find out how many numbers are true, because in the problem, the number of truths are not known. And then we like to see, say, count the number of true statement and pick out who is the driver. So eventually, all the permutations here are valid solution, okay? So say I put this test function onto the first candidate. This will give me like 2 statements in the 4th statement are true. And in this case, the plumber is the driver. Okay, you do that thing for all the candidates, and then it would give you the valid solution set. And then you group by the number of the solutions by a number of true statement, and you have such a result. So 2 means if I have 2 statements in the 4th statement are true, then either plumber or carpenter can be driver. Okay, now let's go back to the problem again. So this problem is kind of tricky. So it gives you a sentence at the end, and it looks like it is a comment, but it's actually a condition. So to get the final solution, we need to have a unique answer. So to get the unique answer, the thing is, we have to look at this line, because in this line, regardless of which statement is true, you have only Baker as driver is the only condition, is the only solution. So if you want to get a unique answer, you need to have Baker as the driver. Okay, there is another one here, but it's quite lengthy. I put it here like a bonus problem. So if you want to do that in office hour or community, we can discuss that in very detail. So it's kind of long problem you can see, but the code is actually quite beautiful. It's kind of thing to get you to advanced programming skill for this type of problem. And then let's move to the graph theory part. So this is from Weissman's illustrated theory of numbers, which is, I think, is the most beautiful math book in the market. There is many combination between number theory and the graph theory in this particular book. So you are lucky to have Mathematica have like working on the heavy lift stuff for this one. So there's one particular one case for the Hess diagram. It shows for basically if I have 240 is divisible by 720. You put the link here, right? And 80 is divisible by 240. But we do not put a link between 720 and 80 because we want to keep all the divisor information in this graph. And this is called transitive reduction graph, which is typically, it's proven to be NP hard for a directed case. Because we have this function directed built in, and also I have committed this one to Wolfram Function Repository. It's really easy to generate this type of graph, and it's kind of handy for lots of illustration things in his book. And the other part he used very often is called modular dynamics and plus graph. So let's take a look at quite a straightforward problem. If you have computer at hand, is 888 a valid three-digit ending for a cube? So this problem is absolutely, you can do that in one line in Wolfram language. Say you just cube everything from 1 to 999 and take a mod 1000. So this will give you everything you need, right? And because we have computers at hand, probably we want to explore a little more than what was just asked in the exam question. So is it like 889 a possible candidate for a cube, ending the ends of a cube? So if you look at this one, you basically do everything and remove the repetition and compute the length of all the candidates. It's 505, which is much less than 999. So it is quite easy to imagine that not many numbers are valid. You definitely will lose something. So if you just remove the length function, you absolutely can check if 889 is there. Okay. The other part is, say I was given a number, say 123, and I cube it, and I take up the last 3 digits, and I cube it again. What kind of dynamics do I have? Is it going to back to 123 at some point or not? So if you do that for all the numbers, just map itself to the cube, what you have is a modular dynamic graph. And if you do that for all the numbers from 1 to 999, that's what you have. This is a very interesting graph. It's one graph. Okay, if you drag it, you can see it's one graph, but it has many isolated islands. So you want to study, say, given a number, is which graph it belongs to. All right, it's a very nature question. We have find graph community function. It's a very useful one. There are many information about it and quite a nice example. And it's typically useful for these isolated stuff. Okay, and then you can do a random choice, and it would show you these vertices or nodes belongs to a particular graph. You can just randomly choose that again. And if you have any vertices or a group of vertices belong to the same graph, you can just use one or everything altogether in a weakly connected graph components function. So this one will give you a graph like this because everything is isolated. So in my case, putting one node or a list of node here will give you exactly the same result. Okay, let's take a look at the example. Say I have this one, okay, and using weakly connected graphs to look at it. Okay, what we have here is something like this. Okay, this is the most useless graph we have because everything ending 0, you cube it, it always becomes 0. So this 0 is the black hole, and they're quite obvious, and intuitively we can get this conclusion. And what's more interesting is graphs like these, and we can just grab it and plot it. This is quite a big graph, so I just use image and plot everything and only take like a quarter of it so you can see what's going on. Say I have a number 906 and I put it into my machine, cube it, and it gets 416 as an ending 3 digit. And then it will orbit to some number and it comes back, but it will never goes back to what you have in the input. Okay, I have a particular interesting application here. It's a manipulated application. It returns a set of graph given a number of nodes. Say if a graph only contains one node, for example, 249 cube, and you get 249 in ending. So it means it is a fixed point. So these are all the valid fixed point you have. And given that a graph with 25 nodes, what do we have? It's quite interesting. It will, for some number, it goes to 125, and then it loops back. It's new like a black hole. And that's what we have. And we eventually have only 4 graphs satisfying this condition. And you can play around everything here. This is included in the notebook attached. So just feel free to play around with the parameters and you'll see what's going on here, okay? Okay, let's go to the last part. It's asymptotics, which I think is the most interesting part, parallel to integral part in Mathematica. So if you recently watch the Squid Game, you probably get what this means. It basically shows what 2 kind of functions in Wolfram language that handles things goes to infinity or approaches to infinity. It does not give you sort of exact thing because lots of functions are quite difficult. It's just like you do Taylor series. You can just approaches a function, maybe arbitrary precision, but you always have error term, and you can decide what's the level order you want to approximate that. And the limit is simply this thing, and eventually you let n goes to, you basically put infinity that and check out if these things goes to 0 or diverge in the as n approaches infinity. And discrete asymptotics basically gives you how fast and then what's the path it will go through. Eventually it diverges or it converges. So for example, there are many like famous series or constant or functions are supported in discrete asymptotics. And you can see there are many ways you can use this thing to compare or just to get a result directly from it. And for example, say harmonic numbers. Harmonic numbers are the sum of reciprocal of natural numbers, like 1 plus 1/2 and so on. It's just like this. It diverges at the rate like log n for the first order. And the amazing thing, and make this part very useful for all kinds of problem I'm solving on CRUX, or this particular monograph about asymptotics on the CRUX, is it supports the sum of sum. This is a very important thing because lots of problems looks like this, and you want to understand the divergence of how fast it grows as the n approaches infinity, and the sum also approaches infinity. And so here, for example, if you have harmonic numbers, so this thing means a double sum. So 1 plus 1/2 plus 1 plus 1/2, 1/3, and so on. So it's like a stair, like a pyramid. You goes infinity, and this thing grows like n times log n. Okay. There are any other functions also on the sums also available in this function, so you can play around it. And yeah, so this is the screencast in the meme. And then let's look at some of the equations, monster equations that can be easily solved with this asymptotics. So most of them either looks like a 0 over 0 type, or this type of problems probably you can use with Stokes-Cesaro theorem. It's like the discrete version of L'Hopital rule. So if you just do simple variable, you define function that replace this part and plug it directly in discrete asymptotics and simplify that with together. This is the expression you have. And if you take the limit of the above expression, usually it's much simpler than this. Or you can just straightforward see, as n goes to infinity, some part easily go to 0. So this is what you have, and you can basically find the limit by looking at stuff. Okay, so if you take the limit of that, it gives you e. Also, if you want to directly do that, it also works. It works for this thing. And if you have some functions like this, and if you know how to rationalize the denominator and make it look like this, kind of neat, and directly put into asymptotic sum, it gives you a very beautiful expression. And you can immediately see that as n goes to infinity, the limit of this expression is just that. And you can see n goes to infinity, 0, 0, and what you have is 1 over square root of 2. The last example here is about the sum of sum. Because if you take a look at ON here, it's a large sum. Okay, though it is it's a product, but it's the same as sum if you take a log. Okay, so this type is same as sum over sum. So if you want to resolve this one, you can first find the asymptotic sum expression for ON. That's this part, and you plug that in the function. It gives you the result immediately. And use that as a function of n and directly put into ON. So it's 2 times this ampersand, the percentage sign. It is this part. What you have is e to the polygamma 0/2. Okay. Then you full simplify that, you get a very beautiful result. It's e to the power of Euler gamma. That's usually the correct result, because these equations are very beautifully designed. Usually you have a result including like zeta function or anything including important constants in special functions, then you're very likely to get the correct result. Okay, I will spend a very limited time about and the last part. I curated recently. It's quite a beautiful application of this to a very important constant. Okay, so this is what we have. It's called a hidden E in Pascal's triangle and more. So there's an E in Pascal triangle. You can follow Dedekind cuts. The link is curated here. You can click that and watch that on YouTube. It basically says if you make a product, so you do product along this line and along the seventh line, you multiply them together and it divides the product of the middle line squared. So it's this one. And as n goes to infinity, you have E. Okay, you have E. So the technique used in I'm not going to too much about the proof, but the technique used inside is he does division along two diagonal directions. So to program that in Wolfram Language quickly, I use this way. So padding 1. So let me show you quickly about how it works. So you have a triangle and you pad 1 first. And once you pad 1, you can do row-wise division by doing this. You take out this part and it divides this part. Because the two arrays are of the same size, same dimensions, Mathematica automatically does element-wise division for you. And what you have is here, okay? And then you take it. You take, because you don't want ones here, you take this from like 1, 2, 3, 4, 5, 6, 7. So like a stair, grow like one length per level. So this way you remove the 1. And you do that again for this triangle. And now you pad 1 to the left. So this time you do this. Once you have this line, and you pick this array, divides this array. So eventually you will have something shown here. And I can show you the dynamic stuff. It works like charm. Okay, then you observe that for example, let's see a row with 10. So we have 10 elements here, all right? And 11 is 1 plus 10. So eventually you have the products of this row is 1 plus 1 over e to the power of n, which is the definition of e if you take n to infinity. So that's everything you need. Okay, so the last part is, because he was doing that with a hand, you really need some skills for you to simplify the thing. But if we do that directly, well, in Wolfram language, you can just directly multiply all the binomials. You have like very big expression, including some well-known special functions here. And then you define that function, you directly compute the limit, it just works. And what's the Riemann zeta function here is if you do that thing and asymptotically find what's hn for n goes to infinity in the first level, in the first order, what you have is here. And you take a logarithm, well, there's something look like this. This thing and this thing. Look at it. Isn't it amazing? You have zeta function, take a derivative at -1, and this times 2 again. And you have exactly the expression here. I don't know why it works, but I'm still working on this book. But the glacier constant is quite important because it shows this identity. Okay. And I think this is the conclusion of what I'm going to present in this topic. And hopefully you like it. And then let's move to the Q&A session. And feel free to write your question in the poll, in the chat room here. Yeah, also there are some like other examples for you to play around the Euler film formula with a Mobius function over K. And this is also supported in like zeta 1 and zeta minus 1 stuff. Yeah. And this is the conclusion for for the Euler formula. Yeah, it's also supported symbolically as n goes to infinity. So there are many interesting what you call it, analytical number theory stuff and the special function related, tightly related to this topic. So I was working on this book. To be honest, if you don't have anything like the Wolfram language support here, most of this book is very dry. It's always about derivation, lots of important equations, but just do that by hand is just torture. So yeah, if you work with this thing, it's just you way happier life, and you can push the book much faster. This thing, I think each thing is okay. Here's the question from Debrota. Is there a list of some Weber constants that arise from number theory on the integers? Yes. I think if you go to how you spell it? Sure. Yeah, there are many mathematical constants here. Yeah, there is a big session about how these things are related, like Catalan, Kimchi, Glacier, stuff like this, golden ratio. It all eventually comes together. And some of the thing is usually represented in zeta function, say like zeta 3, it would be important constant, which is usually if you are into like probability, you know what I'm talking about, like 1 over zeta 3. It is the probability that you choose randomly 3 integers from, you know, the set of natural numbers, and they are co-prime to each other. So it's just crazy thing, pops nowhere, and then you have zeta function. So it's a very beautiful area. And for this type of problem, typically in CRUX, this session, there's a very beautiful monograph on asymptotics, and it shows you how most of the interesting stuff related. Even giving you a function that had nothing to do with E or pi or zeta stuff. Yeah, so it's quite amazing. I'm very pleased with this feature in Wolfram language, because I have tested many problems there. It just to give you a solution instantly. So yeah, it's kind of happy stuff. Yeah.
All right, that might be all the time we have. I worry we're going to be getting too close to the end for getting cut off. Is there a best way for people to reach you if they have further questions?
Yes, you can chat with me. Also, you can be very active on community. I'm there all the time, write articles. So if you are interested in analytic number theory stuff on everything here, it'd be very nice if we can just discuss on community. And typically for this thing, circular inversion, I spent many time on that to make the documents self-explanatory and put interesting contest problems there. So you can just see how to extend the result. Usually they ask you only find some particular thing, but this one works in general case, like Abello's and the circle of Papas and Steiner chain here. Typically this session, I like it a lot. It's about pencil of circles, and it gives you very detailed explanation about why Steiner chain works. And circular inversion also closely related to another sister function about inversion curves. So they are kind of interchanged, but this design of circular inversion, it works much better for Euclidean geometry problem solving. Typically you see in all kinds of contests. Yeah.
Okay, thanks very much, and thanks everybody for coming. We're going to shut the talk down here in just a moment.
All right, bye-bye.